Hello and welcome everyone to the sixth installment of Earth and Planetary Science seminar series. Good morning, good afternoon, good evening to all, depending from where in the world you are joining in this seminar. And so, Institute of Innovation, Research and Education for Earth and Space is an amalgamation for the Earth and space community, for the community of Earth science and the surrounding domains of some young scientist, which in mind has a vision to spread and popularize the earth science and its related domains. So this lecture series is just a beginning of a long-term plan in which many more exciting talks and scientific as well as research related activities are yet to come. So I am Subham Sharkar, postdoctoral fellow at Physical Research Laboratory, Ahmedabad, and a founder member of IIREES. So today, let me have the pleasure to introduce Ms. Torsha Sengupta, researcher at IIT Kharagpur, and also a member of IIREES, to host today's seminar. Over to you, Torsha.
Thank you, Shubham. Hello. Today here we again meet for another exciting seminar organized by IREES. For today's program, amongst us, we were pleased to have Dr. Chandreyee Goswami Chakrabarti. Dr. Chakrabarti, she is presently a research assistant in the Institute of Rock Structure and Mechanics, Czech Academy of Science, Prague. She has done her PhD from University of Calcutta. Her research topic was active faults and crustal deformation in parts of the frontal Himalayas. She was actively engaged and she is actively engaged in teaching and researches, and her topic includes a diversity in nature. It starts from paleoseismology, GIS, and remote sensing to low temperature thermochronology. Today, we will be discussing another interesting topic, a seminar delivered by her. It was on earthquake studies, its importance and role as an earth scientist. Without much discussion about what is the topic and what again, I will like to invite Dr. Chandreyee Goswami Chakrabarti for delivering her presentation. And I will invite her, and now I will pass the stage to her. Thank you.
Good afternoon, all of you. Thanks, Tosha and Shubham, for introducing me and thanks to IIRS, to IIREES to invite me for sharing my opinion, my research experience with some very good young minds, students and young researchers. So I'll start my presentation, and I'll discuss about what is earthquake and how in today's world it's very important to study older and present scenario of earthquake in different parts of the world, and how we geologists uh, can uh, can be useful in doing this earthquake research. So as I have already told, today's topic is earthquake studies, its importance and role of earth scientists. So this a few months back in February, world witnessed a very big earthquake in Turkey-Syria border, and till now the death toll count has exceeded 60,000, more than 60,000 people. And from all over the world, there is a lot of activity going on to provide them aid in different way. Turkey being the part of NATO, and it is considered to be the one of the, as it is in the border of Europe, the whole European community started pouring in with different aid. But Syria is not so lucky because there are, due to the different war conditions, Syrian air, um, there is some the restrictions in the airspace of Syria, but still people are trying to get them to provide help to both the countries. And we have seen many videos and all about the earthquake. And it is estimated that there are more than 500,000 detectable earthquakes in the world each year. 500,000. And among them, 100,000 can be felt, and 100 of them cause damage. If any of us go to USGS website, we can see each and every minute there some earthquake is recorded there. Till date, the world's deadliest recorded earthquake occurred in 1557 in central China. That time the population of the world was much less, and it struck a region where most people lived in caves. But that earthquake caused collapsing of their dwelling, and the estimated death toll is 830,000 people. So in Syria, Turkey, nowadays it is 60,000 people, the death toll, and that back at that time, it was 100,000 people. So we can imagine how big it was. In 1976, another deadly earthquake struck in Tungsten, China, where more than 250,000 people were killed. So where and how this earthquake happened, and so now we'll watch another small video.
A series of powerful successive earthquakes struck the Turkish-Syrian border on February 6th. The first and most powerful was a 7.8 magnitude quake.
This region certainly hasn't seen an earthquake this size in centuries.
Destruction followed as aftershocks hit the region. Then a second 7.5 magnitude quake hit in the afternoon, followed by its own series of aftershocks. In their wake, a humanitarian and economic crisis. Thousands of people are reported dead, and even more are still missing. It's not the first time this region has suffered a violent quake, and it won't be the last. To understand why, you have to look under the surface, where three tectonic plates converge. Together, these plates cause a unique and potentially devastating type of earthquake. The first quake was located here, 11 miles under the town of Gaziantep, Turkey. 11 miles may sound deep, but that's actually shallow for a major quake. The town is especially vulnerable because it sits near the meeting of two tectonic plates. Tectonic plates are massive slabs of rock on the Earth's crust from 10 miles to 160 miles thick that are always slowly moving.
You can take the Earth and divide it up into several large plates that are all moving around each other, and most earthquakes occur at the boundaries between those plates.
This one is called the Anatolia tectonic plate. It's actually a microplate due to its tiny size, and it's constantly under pressure. That's because it's being pressed upward against the Eurasia plate by the Arabia plate. That pressure is squeezing the Anatolia Plate westward, where it faces even more friction from the Africa Plate, which is also moving upward.
The Anatolian microplate is caught in a vise between the Arabian plate moving to the north against the Eurasian plate, and this small plate is being pushed aside as a result of that motion.
That means the boundaries between the Anatolia Plate and the Africa and Arabia plates are trying to slide against each other as the Anatolia moves to the west and the Africa and Arabia move to the east. These borders are called strike-slip faults. And when the friction builds up between the plates as they're pushed in different directions until it's too much, they slip. That's a strike-slip earthquake.
The strain will build up and finally it will rupture and release all that accumulated strain in a large earthquake.
That's what happened in Gaziantep, resulting in that 7.8 magnitude quake. USGS estimates that the strike slip occurred along about 100 miles of the fault, about 20 miles shorter than most strike slip earthquakes.
These are significant earthquakes for this fault system, and so that is probably an accumulation of 300 to 500 years worth of strain that's built up since the last earthquake.
Experts say the energy released in that slip is comparable to that released during the explosive 1980 Mount St. Helens volcanic eruption. The same thing happened 9 hours later in Akinozu, resulting in a 7.5 magnitude quake. This one was just 6 miles down. More than 285 aftershocks have followed both quakes. USGS has called the area tectonically active and unstable.
This region is certainly one of the more complicated parts of the world because there are 4 different plates interacting. So it becomes a region with very complex tectonics.
Those complex tectonics are responsible for a long history of devastating quakes, like this quake from 1966 that killed over 2,000 people.
Towns and villages in 19 provinces are almost totally destroyed.
The 600-mile North Anatolian Fault produced 7 large strike-slip earthquakes from 1939 to 1999. And 3 earthquakes of magnitude 6 or larger have occurred within 155 miles of Monday's earthquakes since 1970. But there hasn't been a large earthquake since 1999.
Because this region hasn't seen a large earthquake for a while, it was overdue.
That 1999 quake was a 7.4 magnitude and caused an estimated 17,000 deaths. For now, USGS estimates there could be billions in economic losses.
The biggest thing is the destruction and loss of life, and it's going to take them years for recovery.
But will there be more disruption if the 2 quakes spark a third? Experts aren't sure.
It may put extra strain on some of the nearby faults, or it may relieve some of the strain on the nearby faults. So it'll take some time to figure out whether further earthquakes are more likely or less likely in this region.
But due to the 3-plate convergence, it's not a question of if there will be another earthquake. It's a question of when.
So, it's not a question of the place, it's the question of when. So, that tells us that now we are able to identify the places of earthquake which are vulnerable to earthquake. And to be very specific, nowadays, these earthquake geologists, they can find the exact place or the exact faults on which an earthquake may occur. But the question is when. So what is an earthquake? Earthquake is the shaking of the surface, as we all know, due to the sudden release of energy in the earth crust. So there is the question lies, when will be this sudden release will happen? Or how much sudden release of energy can cause a devastation or a surface rupture. As we can see different in these photographs, this kind of where the devastation from the underground comes into the surface. Then this kind of uh, calamity or hazard happens. So the release of accumulated elastic strain energy by the sudden rupture of the fault is the cause of the earthquake shaking. So here there is a focus where on this fault uh, the energy starts releasing, and the place where this energy comes in the surface, we call it epicenter. And these kind of fault scarps are present where a fault plane exists. So these places can be identified, monitored, and this strain accumulation, everything can be obtained, can be uh, documented by different type of by in measure of different scientific research. So earthquake is considered as the worst natural hazard. Why? Because it has an impact over a large area, causing destruction on massive scale, loss of human life and property, and the most important thing is the devastation is quick and sudden. Because till now we don't have the capability of uh, saying the exact time of the earthquake, and thus there is no time to escape. So earthquakes happen every day, every hour, somewhere in the world. But there are some places where earthquake is evident every now and then. For instance, all of us know that Japan is such a place, or the Circum-Pacific Belt is such an area where earthquake happens each and every hour or each and every day. Like on the San Andreas Fault, uh, it is monitored every day. There are some very small shocks, but not everything causes devastation or calamity. But yes, that happens every hour, every day, somewhere in the world. So, as you have already seen from the video, the geological and tectonic setting of this recent Turkey-Syria earthquake. Look, whenever an earthquake happens, then immediately from USGS and other organizations, we see where is the epicenter, where is the focus. As we know that shallow focus earthquakes are more devastating because it is near to the surface. And so we need to know the geological and tectonic setting, tectonic plates, their movement, their setting, and in that particular area, how they are behaving. Like in the video, we already saw that this Anatolia plate, which is called a microplate. And here we can say that there is a triple junction between African plate, Arabian plate, and Anatolian plate. Actually, the Anatolian plate is a small plate which is now in making. So, and on this boundary between all these plates, there are Dead Sea transform faults. So there are like left lateral strike slip fault that accommodates the relative northward movement of Arabia with respect to Africa, and the northern end of the Dead Sea transform fault truncates at the East Anatolian fault which is another major zone of left lateral strike slip fault. So on these transform faults and on the strike slip faults, there is always an accumulation of stress. So the Dead Sea transform fault and East Anatolian fault meet at the Marash triple junction in this area. So
Can you
yeah,
just make this full screen, because it is not coming. I mean, it is not coming as a full screen.
this
Presentation.
It is.
Just click on the slideshow button. Probably it will come at that time.
I clicked on it. Now?
Not yet.
Okay.
Madam, you have to present the full screen of yours from Google Meet.
Okay. Just a minute. Your entire screen.
Yes.
Share. And then now?
No, nothing has been shared.
Why? Not now?
Nothing yet. Can I just close the share screen and then share it as afresh? Probably it will.
That is what I wanted to do. Stop sharing now.
Yes. It was just.
Now?
Yes.
I did the same thing, but that time it didn't happen.
No, it's still the slide version is not coming. It is coming the PowerPoint window only.
Why?
Because it is. I mean.
Ma'am, if I may.
Yeah.
You can click the button next to the minimizer thing. Bottom right hand corner. There's a thing
I'm
of
clicking that. I know that.
Yeah.
This one. I am seeing it on slideshow.
Yeah, but you just presented the PowerPoint tab, not the entire screen.
No, I presented the window.
Yeah.
No, that's why.
You have to present the entire screen.
Then in the entire screen, my entire screen. Good.
Yes.
Okay. Now it is
Share.
showing me, right?
You have to click what you are seeing in the entire screen window. In the white window, you are seeing yourself in Google Meet. Yeah, click that. A blue highlight will come.
Share. Yeah.
Now share.
Now?
Yeah.
Yes.
Now you can see that.
Now it's okay. Now it's okay. It's perfectly fine.
Okay.
Okay. Thank you.
So, sorry. I'm so sorry. Okay. So this Turkish Syria earthquake. So could you watch that video?
Yes, ma'am. That was fine.
Okay, fine. So it is not very. Okay, so this tectonic setting, you can see from here, this The scenario here about triple junction of Arabian plate, African plate, and East Anatolian plate. As I was saying that this East Anatolian plate is called as microplate, as it is making. This small plate is in making. And so the whole strain, the stress is adjusted in different transform faults and the strike slip faults. And in the left corner, you can see that comparison of North Anatolian and San Andreas fault. So here, there's a similar slip rate, age, length, and straightness. So these strike slip faults, these are important because they are very shallow focus faults. And so when the stress releases on these faults, the devastation can cause havoc. And there is another point that as these places are on the coast, and this along this west coast of America, and as you can see, these places in Turkey and Syria are very, very overcrowded. The population there quite very good, very much populated, because of these coastal regions always are good for living. So this when any calamity or hazard comes in these places, so due to this high population, the effect is very high. And what about our India? We know that a major plate boundary, actually, 3 major plate boundaries surround India. And so we have many earthquakes in last, say, 100 years. The northern boundary of India, there is the biggest seismically active, one of the biggest seismically active region of Asia, that is Himalayas. In western part, there is this Arabian plate boundary, and in eastern and southeastern part, there is the Indian and Burma plate boundary. So the vulnerability of, but there is also major cratonic part in India, which is very stable. But the border parts are really unstable and vulnerable to earthquake. So we are talking about the biggest earthquakes of the world. Now, after 2 months of this big earthquake in Turkey, we are all are talking about this devastation, the generation, the awareness, generating awareness among the people. And we all know the people who are now in their 20s and 30s, they may remember the havoc tsunami in 2004, Sumatra earthquake, and recently there is Gorkha earthquake in Nepal, Kathmandu, then the Sikkim earthquake. But there are many major earthquakes which happens in offshore, like Sumatra earthquake, and causes tsunami. But it is the 1950 Assam-Tibet earthquake, which is considered to be the strongest earthquake ever recorded on land. So that was 8.6 Richter scale earthquake. And I want to show you one video on this 1950 earthquake. Actually, comparing to the other places of the world, our recording and documentation is very poor. There was a big earthquake in 15th century and we don't have that much of good documentation. So I want to show this one video on Assam earthquake. Uh, So, this Assam earthquake is the biggest earthquake recorded on land. The epicenter was on Mishmi Hills, and the course of the river Brahmaputra changed, causing huge flood, and the whole Dibrugarh town was washed out. So, but you know, how many of mainland Indian people know about this devastation and are aware of this Himalayan, this Assam earthquake is the example of uh, a big convergent plate earthquake, but we are not that much aware of this kind of devastation as we should be. So, plate tectonic framework for earthquake, as we know that divergent and convergent boundaries, there are some transform fault boundaries like these, and in this divergent boundary also they are mostly shallow focus earthquake. In convergent boundary, there are in this kind of thing there is shallow and medium focus earthquake, and all these parts of the world are quite vulnerable to earthquake, like as you can see that this is shallow focus and these are the deep focus earthquakes, and mostly in these subduction zones we have this in the oceanic plate boundaries there are the shallow focus earthquakes which causes tsunami, and they are very frequent all on the Circum-Pacific area. But as you can see, this transform fault boundary and the strike slip fault boundaries are common in California, San Andreas fault, and also in Turkey. There is a very big, as you can see, this strike slip boundary is, the surface rupture is hundreds of miles, and it causes a big vulnerable, it creates a large place vulnerable to earthquake. And also, along with this plate boundary thing, there is also elastic rebound as a cause of earthquake. What is that? It's slow storage of elastic energy over time. That could be due to deformation. Sometimes it can happen due to overload, maybe big ice sheet or something. So forces holding rocks together are overcome, displacement by elastic rebound, and thus these force shocks and aftershocks and this kind of landform may happen. So how do we locate an earthquake? Energy is first released as focus, as slippage. This exerts strain along the fault, producing more slippage elsewhere. This propagates as energy, and that creates shaking. So, how much energy is released and produced in earthquake? So, this is the Richter scale, and minor earthquake felt by human is between 3 and 4, and you can see that it is the same energy as the large lightning bolt. This average tornado kind of energy is released when it is between 4 and 5. This Hiroshima atomic bomb equivalent energy is released between 6 and 7, like 1994, Northeast earthquake, 95, Japan earthquake, then world's largest nuclear test, Mount St. Helena eruption between 7 and 8, like in these earthquakes. And now you imagine about this 8.3 earthquake in 1950 Assam. And it has even more energy than world's largest nuclear test or Krakatoa eruption. That's the biggest earthquake till now is in Chile, 1960, which crossed 9, between 9 and 10. But now, we really don't use this Richter scale for measuring earthquake. This modified Mercalli intensity scale earthquake is used to understand the devastation, where this is the 12-point scale, where 12 is damage total. Lines of sight and levels are distorted, objects thrown into the air. So this 7.8 magnitude earthquake in Turkey is considered to be the Mercalli scale 12 earthquake. So, even more than that, even the Gorkha earthquake is also 12 Mercalli scale earthquake. So now the geologists, the use of the knowledge of geologists to, I can't say it's preventing the earthquake, but it's preventing or minimizing the devastation, or it's the making awareness, creating awareness with the geological data and knowledge. Earthquake cannot be prevented, but if we know about the places and the how often the areas are vulnerable to a big earthquake. Like the video on the Turkey earthquake, the geologists were saying that from 1999, there was not a very big earthquake in that region. So you can see that in 24 years, there has been a big earthquake in that region. So the strain accumulation, if we can calculate the strain accumulation and we can calculate that how frequent that area, that energy can be released in that area, then we can predict not exactly the date and time, but in how often that area can suffer a major earthquake. So for those things, first come the tectonic geomorphology. We all study geomorphology, but this kind of geomorphology is related to that area where the landscape is formulated by the deformation of recent earthquake. What do I mean by this word recent earthquake? That recent earthquake or active tectonics is considered to the deformation happened in approximately last 10,000 years. Or in some places, it's considered to be till the Pleistocene time. Actually, the Quaternary time, the deformation in the Quaternary time is considered to be within the active tectonic domain. So this tectonic geomorphology helps us to understand the deformation and its effect on the present day landform due to in the quaternary time. So the fundamental objectives are use of the landscape to establish tectonic conditions of surface uplift and surface deformation. Use tectonic information to predict landscape response. And it is a coupled system with climate. So tectonics and climate both help in forming a present landscape. As you can see in this figure, this surface is folded. The river flows this side, but this surface is tilted in the opposite direction of the flow of the river. So that helps you understand that there must be anything wrong, there must be any deformation. And as these landscapes are not very old in terms of geologic time, so there must be active tectonics which made this kind of tilting of the surface. So these time scales and orogenesis in a classical models of tectonic forcing and landscapes responses, like how a landscape responds with the tectonic movement, like rock uplift, and then it is it's eroded, and again the uplift. So upliftment and erosion has formed with the time. It is a kind of harmonic type thing, like with once it uplifted and then again it's deformed. And we see different geomorphic indices. That one geomorphic index is river, one is the fluvial terraces, and if you can see, there are offset of streams along this line. the streams are offset, and there are the beheaded streams. So as I just told you, the stream or the rivers is one very important geomorphic index whose behavior helps us to identify whether they are tectonically governed or just the climatic thing. Like if we have the fluvial terraces with different height and it doesn't match into two sides, then there must be some deformation or upliftment in one side in comparison to the other side. So the terraces can map uplift pattern like this. We know this kind of ramps and hinge and graben from the structural analysis, but we can see these things from the terrace uplift also, like this. This is the photograph I showed you is kind of this kind of tilting is there. So these river terraces help us to identify whether there is any deformation, like this place. This is a digital elevation model of that area. This is Tista River. So you can see these lineaments and all. And when we draw the sections, we found the surface is folded like this. And you can see the lower photo of how much fold, how, terribly this surface has been folded. So if we work on this surface only and their sculpture, then we can see from this the behavior of the rivers and the surfaces, we can identify if there is any older tectonic activity. So these river profiles, you can, when you see this kind of river profile, you can see the slope changes abruptly. So there must be any fault or something in these places where the point where the profile changes its slope abruptly. So we make this kind of river profiles to understand that. So this is this kind of terraces which are not parallel, which are offset from this terrace is offset here. So we can see this kind of, from these fluvial terraces, we know there is a fault. And finally, we can build a geological, geomorphological map which helps us to identify the arrangement of different faults and tectonic movements in a particular area. So this is another place very near to the epicenter of 1950 Assam earthquake, where you can see in the quaternary surface, quaternary area within a very flat Brahmaputra river valley, Lohit river valley, there is such a big hill. And how come this hill built in this quaternary time? This hill, the height of this hill is, as you can see, more than 500 meters. So in last, say, 200,000 years, this more than around 600 meter upliftment has been suffered. This area has been suffered. So how big stress, how much stress can be accumulated, and where are the places where this stress is released? We need to know those places because those are the places of the future probable earthquakes. So we make this kind of geological, geomorphological map to identify the river behavior. You can see that there's a fold axis, and this is a ramp anticlinal fold over a thrust plate. And I go back to this slide. So this is Mishmi thrust, which is in the boundary between, which marks the trijunction boundary between Indian plate, Eurasian plate, and this is Burmese plate. So this is the Naga Shupen thrust, and this is Mishmi thrust. So, and as I told you that the epicenter of 1950 earthquake was on Mishmi Hill. So this big land earthquakes can happen in these areas, and these areas are one of the most seismically active area in Asia. And not only that, it is the fastest moving part of Indian plate. So then, after tectonic geomorphology, there is paleoseismology. So what is paleoseismology? When we talk about the earthquakes, we talk about seismology. That is present day seismology. As in the inaugurating video, Moinak showed you that seismically, India, the zones in India, that is on the basis of the present day seismology. But what about the paleoseismology? This paleoseismology is the old seismic activity, and where do we get them? The investigation of individual earthquakes decades, centuries, or millions after their occurrence. And we study these ancient earthquakes, geologic study of the past behavior of active faults. And why this is important? Because this is the best method to determining the rupture history on faults with moderate to long repeat times. And that gives us the recurrence interval of a particular fault. And we have this high resolution topography from LiDAR, and from there we find the exact position of the fault, and then this offset of the channels and so many things, and then we find these trench sites on the exact fault. We do the trenching to open up, to see the ruptures, to the deformation on the sediment or the rock itself. So the trenches are often extended to ensure that all major fault plays are exposed. Ideal paleoseismic sites have continuous deposition at fairly constant rates of material with large amount of data set. So, and from this, if we can measure the displacement, then we can measure also the rate of the displacement with time and the recurrence interval of an earthquake. As you can see from a trench, that this offset of this bed, and we measure this, and we can calculate from here that how big that earthquake was. And so we can estimate that in future what is the probability of a big earthquake from this place. This is from a thrust fault where there you can see the folding on a thrust plane of the bedding planes. So the earlier was on the normal fault, and this is from the thrust fault. And then we date them. So in this earthquake study, geochronology plays a major role. What are the different kinds of geochronology? First, we see the historical data, then we do the radiocarbon dating. If we get the either the charcoals or carbon-rich clays or something, but it can date only up to 50,000 years. So then what? Then we have vessel dating, optically stimulated luminescence dating, where we sample the materials so that it doesn't catch the present day light, because the principle of vessel dating is when did that material last obtained light. So it is the depositional age of a particular bedding. And we also date the offsets of thrust faults and inferred versus actual exhumation rates for models of simple exhumation. We do this low temperature thermochronology. Last week's lecture was on this kind of thing, where there was apatite, helium, dating methods and all. So we date for this exhumation history, we date by apatite, from the apatite zircon and apatite fission track. We measure the exhumation rate, and these are some results from Himalayan exhumation, about the Himalayan exhumation in the eastern Himalayan sector. And again, this was about the vertical uplift. Now this, from the GPS geodesy, we can also measure the actual crustal movement. So this crustal deformation and earthquake, how much strain is accumulated in particular boundary, can be measured from GPS geodesy. So these are some method. There are some GPS stations all over the world which are permanent stations, and some there are across the faults. The geologists do, or the geophysicists do, the survey mode GPS surveys, where we actually measure how much movement in particular time it occurs, and we can see that from these red lines, this is the measurement of this plate, in the Pacific plate, in a particular time. And as I told you, this continuous GNSS, that is the permanent stations, and these are calibrated with the satellites, and these permanent stations are calibrated with those campaign mode or survey mode GPS to measure actually across the fault how this plate behavior, plate moves, or what is the displacement across a fault. And nowadays there is the INSAR also, where coseismic motion detected by CGPS and INSAR. We measure how much deformation in a particular area after a particular earthquake. So you can see this evolution of continuous GPS from 1999 to 2018, and it will show the actual deformation of a particular place of this plate. So they can give the result with 95% confidence. And last but not the least is the electrical resistivity and other geophysical measurements, where the resistivity of the layers is measured to know whether these layers have been displaced across a fault. Like if you can see this, along this fault line, this is the fault scarp, and along this fault line, it is measured this ERT profile, and it shows the exact place of the fault and exact displacement. And sometimes before doing this paleoseismic trenches, they do the ERT to know the exact place of the fault, and then with these paleoseismic trenches, they can obtain the exact displacement. So from this geological map, then this ERT and this paleoseismology, one particular fault is monitored. And also there are some fault monitoring devices where they are put in across the faults, and they act or on the fault surface to actually monitor how much deformation is happening on that fault. In San Andreas fault, people do this kind of measurements, but alas, in our country, where we have such a big plate boundary, but we have rarely till date, as I know, there's hardly 10 trenches have been, paleoseismic trenches have been done in Himalayas. There are some trenches have been done in Gujarat, but this is a huge scope of work of doing earthquake studies, and should be, because we have along this Himalayan boundary, we have many major hydroelectric plants, many big roads, tunnels, and everywhere. If we don't map the active faults accurately and we don't calculate the surface rupture and the recurrence activity of a particular fault, then we cannot minimize the devastation. There is I will finish my talk with mentioning a very good reference. It was the heading of the article is "Corruption Kills" by Roger Bilham. You should search it. It is free. It was published in Science, as far as I remember, Science or Nature. And it showed that the death toll of earthquake is not actually depending on how big the earthquake is. Rather, it is dependent on the corruption and how the planning is not being done according to the scientists' advice. So wherever the death toll is maximum, like in Japan, every day there are earthquakes, but how much death toll is there? Just because they monitor it very well, they maintain the town planning. But in Turkey, in Mexico, in Nepal, people suffer, people die in a lot of number due to this ill management. So we geologists have a great scope in doing this kind of work, and we need, this is the need of this time to think about socially. I mean, this science it has a social impact also. So thank you for listening. This is from the Himalayan frontal thrust, and you can see how big it is.
Thank you, ma'am. Thank you for the exciting talk. It was really a pleasant indeed. Now, before I think our participants will have some question regarding the talk. So
Okay.
let's see. And before anything else, I would also request all the participants to fill up the Google form that was shared via the GChat option. It was a feedback. It is a feedback form. Please share your valuable feedbacks. It will also help us to mark the attendance as well as provide you with the participation certificate. Before going to the questions by other participants, I have some few questions. The one question that you just ended with about the we need geologists for before the town planning in this particularly earthquake prone areas. So, as a very early career scientist, early career geologist, what will be our focus? What is the exact way we could participate in this kind of endeavor, and what is the exact role of the geologist for this town planning, for the initial role? What would be the initial role?
Okay, so this is a very good question, and in our country, it's very unfortunate, but that's till now we separate the study of geography with geology. But what I see here in Europe that it is not like that. So in our perception, this town planning, land use planning are mostly done by the geographers. But as a geologist, we should focus more on this kind of research where there is a use of satellite images and other remote sensing data, and from there, because the geography researchers, they from those data, which are only the surface data, they draw maps, but we geologists understand what is beneath the surface. So until and unless we combine those remote sensing data with the actual sedimentological data and the structural data, this database will never be completed, and we cannot get that. That's where this paleoseismology comes. We cannot get the actual scenario of a particular fault. So, but unfortunately, as far as I know, till now, our main our training as a geologist in Indian universities are mostly on the hard rocks. So more and more people should have the intention, or they may focus, they may work on these sediments, not the rocks. But yes, nowadays it's much more than 20 years back. It's good that it's happening more. It's happening gradually.
As you were talking about paleoseismology, I have a kind of an interest in it because I work on quaternary sediments, that too from archaeological sites.
Yeah.
So I have seen some archaeologists, they are talking about this particular section was under some seismic activity and all. They are not obviously delineating particular fault or something like that, but they are kind of correlating some past seismic activity with the habitation layer, some gap in the habitation layers, like that only. So what extent this paleoseismicity could tell us, not only from the rock record, from the soft sediment record also, and also the within the habitation layer, what exactly it could tell us?
For paleoseismology, hardly we get any rock, because and the deformation in the rock doesn't come on this quaternary active tectonics if it is not exposed to the surface. But it from paleoseismology is a really very good procedure to identify the earthquake in recent years. I mean, from the from the fault scarps to the exact displacement. And for that, it happens, for the normal fault, it's easy. For the thrust and strike slip fault, it's really a tricky thing, but it is confined in the soil layer and just below the soil layer. And if we can identify the surface rupture and consecutive the surface rupture, then it can be exactly calculated the time gap between two earthquakes.
Seismic events.
And from the displacement, this vertical and horizontal displacement, we can even calculate how big that earthquake was.
So it is like we could past calculate that how devastating the earthquake was, how exactly it is.
Yes, and it is done in many places. I have seen in Italy, one researcher, she has done more than 40 trenches to monitor a particular fault. Because in the Italy, there is alpine faults, and also the coastal Italy has many strike slip faults also. So it can be monitored. But in our country, one problem about Himalaya is that it's thrust fault. It's more complicated. And secondly, too much habitation, because these nuances which happens in the upper part of the layers, if it is more habitated, then it may not be preserved.
Yeah, that is another thing, because while working on archaeological deposits, that's what my question is. So probably it will be kind of rubbed off of the.
So that's why this extensive work is needed
to be done.
Yeah.
Okay, now passing on to, if anyone have any question, they can put it into the chat box, either in the YouTube live chat or in the GChat option as well.
Yeah, there is one question. Is the luminescence method applicable where there is a repeated depositional and erosional event? Luminescence dating helps in identifying the depositional event. So if we find that similar kind of sediments are displaced and we date them by vessel method, we can find that whether they are the same bed or same sediment, because it will give us the depositional time. And if it is displaced, then we can mark the how much it displaced. So yes, it is vessel dating gives us the depositional record. Like in a faulted area, due to the bogging of a river, if some clay bed is deposited, we can, from the vessel date, we can determine this timing of the fault, because it is related to the deposition of that particular fault. But no, not the erosion.
So any other question from the participant? Okay, we'll wait for 1 minute probably. Let's see.
Yeah, I have taken a long time.
Oh, ma'am, it was indeed a very good presentation. It's a very informative one.
Thank you for inviting me.
Okay, ma'am, I think Okay,
Yeah.
there is one question by Mahina Sinha. Are there any model to constrain intraplate earthquakes?
Yes. Uh, it is not about model. Like intraplate earthquake is related in many time with the hotspot. Like where I am sitting now in Czech Republic, there is an interplate earthquake, and we are working on that. It's very slow. Seismicity is very low. Nobody can imagine there would be an earthquake, but there is. And there is earthquake swarm. So I don't know about any model. Model is same for locating every earthquake, like this paleoseismology they do here. Uh, like in last 2 years, I have done 4 trenches here. So the model is not like that, but yes, we here the due to this hotspot, there is emission of different gases and carbon dioxide gas, helium gas, and these things. And then we start then look for geographically the geomorphology, and we found this source of this earthquake. So I would not say there is a model, but it can be done in interplate earthquake also.
I think. Oh,
So should we
yeah,
finish here?
I think
I think so, ma'am.
yes.
Mhm.
No one else has some question.
think, yeah.
Yes.
Thanks, Tosha, for hosting the session. Thanks, madam, for delivering such a beautiful talk. And also thank you all the participants, especially Anushka Roy and Moinakshina, to ask a few questions. Just
Yes, that is very nice.
yeah, because we all know as young students we are very shy to talk or shy to pose any questions. We first think that what could the other person. Yeah, Shashank Mahapatra have one
Yes.
question. So Shashank,
Yes.
please post your question in the chat box. Or you could
Or you can ask.
yeah, you could ask you
You
directly.
can ask because no one is talking, so you can
Okay.
ask.
Hello, ma'am. Good evening.
Good evening.
It was such a great presentation. I found it very informative. So thank you so much. So in one of your slides, you showed that how you, you showed a small time series to show the deformation events caused by the earthquake.
Mm-hmm.
So for that, what particular model or software did you use to bring out that time series? I wanted to know because I'm also interested in INSA remote sensing. So I really want to know what
Time
software or
series.
model did you use. Yeah,
Let me see which one you were talking.
I think it
From
was,
INSA?
yes, sir. Yes, ma'am. Yes, ma'am.
From
You
INSA.
one interferogram image you are showing.
Oh, uh, this GPS model is done in Gamete software, and
Okay.
okay.
Okay, ma'am.
So what you work on this or work on INSAR?
No, ma'am. I'm interested in learning this
Okay.
part of science. So that's why, out of curiosity, I wanted to ask
Mhm.
you.
It's nice. Nowadays, it's these things are developing very fast, and people are working it's good, but still you need the softwares which are very expensive.
Right, right. And I think they are also not freely available, so
Yes,
licensed. Yeah.
and nobody gives money to research for research.
Especially with the case of microwave remote sensing, there are few tools that are freely available, and you could do all the works with the available software that are in the market and that you have to purchase. But the free softwares are good with a bit limitations.
Yes, yes,
So to
and
start with,
we have in many places like academic versions, which are quite good.
yeah,
And if one can work, there are ways.
yes, if there is a will, there are ways.
Yeah, if one wants to really work on this, there are.
So with this, I think I should thank all of the participants and especially Tosha and Chandreyee madam to hosting and delivering such a wonderful talk. We'll see you in the coming session of IIREES. We'll be here with another interesting talk like today's. Till then, goodbye, stay safe,
Bye-bye.
stay tuned. Bye.
Bye.
Bye. Bye. Bye.